Welcome to the Deep Dive, brought to you by X9 Intelligence. Today, we're taking a deep dive into the world of quantum computing, specifically Google's new Willow chip.
Okay.
You might have seen the headlines about its mind-blowing calculations.
Yeah.
It's causing quite a stir.
Absolutely, yeah.
It's a significant leap forward.
It really is.
Willow's ability to perform certain calculations in mere minutes. Calculations that would take a supercomputer 10 septillion years.
Yeah, that's remarkable.
10 septillion years. That's longer than the estimated age of the universe.
Okay, let's unpack this a bit.
Sure.
What makes this chip so much faster than traditional supercomputers?
Well, it all boils down to how quantum computers process information. Instead of bits, which can be either 0 or 1, quantum computers use qubits. Qubits can be in a superposition, meaning they can be both 0 and 1 simultaneously.
Okay.
This allows them to perform multiple calculations at the same time, exponentially increasing their processing power. That sounds incredibly powerful. But I also recall that quantum computers have been notoriously prone to errors. Has Willow managed to overcome this challenge?
That's precisely what makes Willow so groundbreaking. For nearly 30 years, error correction has been the biggest hurdle in quantum computing. What's fascinating here is that Google's research shows Willow actually reduces errors exponentially as you scale up the number of qubits.
Wow.
They've achieved what's known as below threshold error correction.
Below threshold, could you elaborate on what that means and why it's so significant?
Of course. Below threshold means the error rate decreases as the system gets larger. Think of it like this. Imagine a system where each component has a small chance of failing. In a traditional system, the more components you add, the higher the likelihood of a failure somewhere. Below threshold, the system actually becomes more reliable as you add more components.
So in essence, they've cracked the code of scalability in quantum computing.
Precisely. And that opens the door to building much larger and more powerful quantum computers in the future.
This all sounds very promising. But what about the number of qubits? How does Willow stack up against the competition in terms of sheer qubit count?
That's an interesting point. While some companies have focused on increasing the number of qubits, Google took a different approach with Willow. They focused on improving the quality of the qubits rather than just adding more.
So it's not just about quantity, but quality as well.
Exactly.
What specific quality improvements did they make?
One crucial factor is the T1 time, which measures how long a qubit can maintain its quantum state or hold information. Before decoherence sets in, Willow boasts impressive T1 times approaching 100 microseconds, a 5-fold improvement over its predecessors.
Wow, a 5-fold improvement. That seems significant. Why is a longer T1 time so important for a quantum computer's performance?
The longer the T1 time, the more complex calculations a quantum computer can perform before the qubits lose their information and errors creep in. It essentially allows for more stable and accurate computations.
So Google's strategy seems to be paying off. They're making significant strides in quantum computing.
Yeah.
But of course, they're not the only players in this field. There's a global race for quantum supremacy, isn't there?
Absolutely.
And China has emerged as a major contender, investing heavily in quantum technology. In fact, their investment surpasses any other country, pouring over $15 billion into research and development.
Wow.
That's triple the amount invested by any other nation. What are some of China's key areas of focus in the quantum realm?
While they're pursuing various avenues of quantum research, they've placed a particular emphasis on developing quantum networks. These networks could potentially revolutionize communication and data security.
Quantum networks. Now, that sounds intriguing, but I also have to wonder, are there any concerns about concentrating so much technological power in one country?
That's a valid concern. The geopolitical implications of quantum technology are certainly something to consider. However, for now, let's delve a bit deeper into the potential benefits and challenges of these quantum networks.
Okay, let's do that. You mentioned data security. How exactly do quantum networks fit into that picture?
Well, one of the most talked about threats posed by quantum computers is their ability to crack the encryption methods that currently protect our online data. Imagine a world where our bank transactions, private messages, even government secrets could be vulnerable to quantum hacking.
It's a chilling thought. It's like the store now, decrypt later scenario you mentioned earlier. Are we talking about a distant future? Or is this something we need to be concerned about right now?
It's closer than you might think. Organizations like HSBC, which handles trillions of pounds in payments annually, are already deeply concerned about this threat. They're actively exploring ways to safeguard their systems against potential quantum attacks.
So what's the solution? Is there any hope for securing our data in a future where quantum computers could potentially crack any code?
There is. Researchers are working on innovative solutions like quantum-resistant encryption algorithms and a fascinating technology called quantum key distribution, or QKD.
A QKD. Okay, this sounds promising. Can you explain how it works and why it's considered unhackable?
QKD leverages the principles of quantum mechanics to create encryption keys that are virtually impossible to intercept without detection. Let's break it down.
Great, let's do that. Because if we're going to be relying on this technology to protect our data in the future, I think it's important for us to understand how it works.
Absolutely. At its core, QKD involves using individual photons, or particles of light, to transmit encryption keys. What's unique about quantum mechanics is that any attempt to observe or measure a photon inevitably alters its state. So if someone tries to eavesdrop on a QKD transmission, they will inherently change the photons, revealing their presence and compromising the security of the key.
So it's like having a built-in alarm system that goes off the moment someone tries to peek at the code. That's a pretty elegant solution.
Exactly. And the beauty of QKD is that it can be implemented using existing fiber optic networks, making it a potentially scalable solution for securing our communications.
That's good news. But fiber optic networks have limitations, don't they? Especially when it comes to global communication. What about transmitting data across continents or even around the world?
You're right. Signal loss over long distances is a major challenge for fiber optics. That's where the limitations of fiber optics become apparent. And that's why, for truly global coverage, researchers are looking beyond fiber and exploring satellite-based quantum networks.
Satellite-based quantum networks. That sounds like something straight out of a science fiction movie. Are there any real-world examples of this technology in action?
Actually, there are. China launched a quantum satellite called MISHIS back in 2016. It successfully demonstrated the feasibility of satellite-based QKD, transmitting entangled photons between space and ground stations thousands of kilometers apart.
Wow. China's really pushing the boundaries of quantum technology. But I understand they're not the only ones exploring satellite-based QKD. What about other countries?
You're right. Singapore, for instance, is pursuing a different approach. They're focusing on developing a global quantum network using smaller, more cost-effective nanosatellites.
So there's a variety of approaches being explored. It seems like the race for quantum supremacy extends beyond just computing power. It's also about building the infrastructure for a quantum-secure future.
Precisely. And this race has significant implications, not only for cybersecurity, but also for global communications and even national security. The stakes are incredibly high.
It's a fascinating and potentially game-changing era we're entering. But before we get too carried away with the geopolitical implications, let's bring it back to Willow and its potential real-world applications. Those septillion-year calculations are impressive, but how will they actually translate into tangible benefits for us here on Earth?
That's the crucial question. Willow's achievement is a significant step towards building a truly useful quantum computer that can solve real-world problems beyond the capabilities of classical computers. Problems in medicine, materials science, artificial intelligence, and many other fields.
That's where it gets really interesting. So let's shift gears and delve into the practical applications of quantum computing. What kind of breakthroughs can we expect to see in the coming years, thanks to advancements like Willow?
Let's explore that further. One area where quantum computing could truly revolutionize things is medicine.
Okay, now we're talking. Medicine always seems to be at the forefront of these technological leaps. How exactly will quantum computing change the game?
Imagine being able to design drugs at a molecular level, using quantum simulations to see precisely how different compounds interact with the human body.
That sounds like something straight out of a sci-fi movie. We'd be able to see the effects of a drug before even synthesizing it.
Precisely. It would completely transform drug discovery and development. We could develop more effective, personalized medicines with far fewer side effects, and potentially even cure diseases that are currently considered incurable.
Curing incurable diseases. That's a bold statement.
Yeah.
I can see why people are so excited about the potential of quantum computing. Are there other fields where we might see such revolutionary advancements?
Absolutely. Materials science is another area ripe for disruption. Quantum computers could help us design entirely new materials with properties we can only dream of today.
What kind of properties are we talking about?
Think about super strong, lightweight materials for building everything from skyscrapers to spacecraft. Or imagine developing new types of solar panels that are vastly more efficient at converting sunlight into energy.
More efficient solar panels. That would be a game changer for renewable energy.
Exactly. Speaking of energy, quantum computing could also revolutionize the field of renewable energy in many ways. From optimizing energy grids to potentially unlocking the power of fusion energy.
Fusion energy. Now that's a holy grail of clean energy that scientists have been chasing for decades. You're painting a picture of a future that's both incredibly exciting and a little bit daunting. What about artificial intelligence? How will quantum computing impact the development of AI?
AI is already transforming our world. But with quantum computing, we could see a whole new level of sophistication. Quantum computers could supercharge machine learning algorithms, allowing them to process vast amounts of data and identify patterns that are currently hidden from us.
So we're talking about AI systems that can learn and adapt faster, make more complex decisions, and potentially even exhibit creativity that rivals humans.
That's certainly within the realm of possibility. It's both exciting and a little bit terrifying, as you said. But that's the nature of any powerful technology. It all comes down to how we choose to use it.
That's a sobering thought. But ultimately, I believe in the power of human ingenuity to use these tools for good. It's like we're standing on the edge of a new frontier, full of wonder and possibility. What do you think, from your perspective?
I share your optimism. I believe quantum computing represents an incredible opportunity for humanity. However, it's crucial that we proceed with a sense of responsibility and a commitment to collaboration.
Collaboration is key. It's not about which country wins some imaginary quantum race. It's about humanity as a whole winning the future.
Absolutely. The breakthroughs we've discussed, from Google's Willow to China's quantum satellite, are the result of the collective efforts of scientists and engineers from all over the world.
And the challenges we face, like securing our data in a post-quantum world, are global challenges that require global solutions.
That's precisely it. We need to break down barriers, share knowledge, and work together to ensure that this transformative technology benefits all of humankind.
It's about recognizing that we're all in this together, that the potential of quantum computing is far too great to be confined by national borders or selfish ambitions.
Well said. It's about embracing the unknown, the uncertainty, the challenges, and the incredible possibilities that lie ahead.
Speaking of possibilities, I can't help but wonder about the specific ways quantum computing could impact the development of advanced AI. You mentioned quantum machine learning and quantum neural networks. Can you elaborate on those a bit more?
Of course. Let's start with quantum machine learning. Quantum machine learning is all about using quantum computers to enhance the capabilities of machine learning algorithms. These algorithms are already powering everything from self-driving cars to personalized recommendations. But imagine what they could achieve with the added power of quantum computation.
So we're talking about AI that can analyze data, learn patterns, and make predictions with even greater accuracy and speed.
Exactly. Quantum computers could enable machine learning algorithms to process vastly larger and more complex data sets, uncovering subtle patterns and relationships that would be impossible for classical computers to discern.
That sounds like a recipe for some truly groundbreaking advancements in AI. But you also mentioned quantum neural networks. What are those and how do they differ from traditional neural networks?
That's where it gets really interesting. Traditional neural networks are inspired by the structure of the human brain, but they're still limited by the capabilities of classical computers. Quantum neural networks, on the other hand, are designed to run on quantum computers, taking advantage of quantum phenomena like superposition and entanglement.
Superposition and entanglement, those are some of the mind-bending concepts at the heart of quantum mechanics. How do they translate into advantages for neural networks?
Imagine a neural network where the neurons can be in multiple states simultaneously, thanks to superposition. This allows them to process information in a fundamentally different way, potentially leading to much faster learning and problem-solving abilities. And entanglement allows for connections between neurons that are far more complex and nuanced than anything possible in a classical neural network.
It sounds like quantum neural networks could take AI to a whole new level of complexity and sophistication. What kind of applications are we talking about here?
The possibilities are vast. Quantum neural networks could revolutionize image recognition, natural language processing, and even drug discovery. Imagine AI systems that can understand and respond to human language with the same fluency as a native speaker, or diagnose diseases with pinpoint accuracy.
It's both exciting and a little bit unsettling to think about the implications of such powerful AI. It raises a lot of ethical questions, doesn't it?
Absolutely. As with any transformative technology, we need to be mindful of the potential risks as well as the rewards. It's crucial that we develop and deploy these technologies responsibly, with careful consideration for their impact on society.
That's a great point. It's not enough to simply chase technological advancements. We need to have thoughtful conversations about the ethical implications and ensure that these technologies are used for good.
I couldn't agree more. Ultimately, the future of quantum computing and AI is in our hands. It's up to us to shape it in a way that benefits all of humanity.
That's a powerful thought. It's both a challenge and a responsibility. And it all circles back to the importance of collaboration, knowledge sharing, and global cooperation.
Exactly. The quantum revolution is not a zero-sum game. It's an opportunity for us to come together and create a future where technology serves humanity, not the other way around.
Well said. And on that note, I think it's time to wrap up this deep dive into the world of quantum computing. A huge thank you to you, our expert, for sharing your insights and helping us navigate this complex and rapidly evolving field.
It's been my pleasure. It's always exciting to discuss the possibilities of quantum computing with such an engaged and insightful audience.
And of course, a big thank you to all of our listeners for joining us on this journey. Remember, this deep dive was brought to you by X9 Intelligence. We hope you found it informative and thought-provoking.
Until next time, stay curious and keep exploring.